Hello there! Today we will be talking about significant figures, scientific notation, units of measurement, dimensional analysis, and density, which are all very important to begin your high school chemistry course. First, let's talk about significant figures and measurement. Now, significant figures have certain rules we have to follow. The first rule is that every non-zero digit in a measurement is assumed to be significant. For example, in the number 42.7, 50.3, and 44, all of the numbers that are non-zeros, so that includes the 4, the 2, the 7, the 5, and the 3, they are all significant. The second rule states that all zeros appearing between non-zero digits are significant. For example, in the first number, 1.3705, the 0 is significant because it is in between the 7 and the 5, which are significant figures. Same with the second number, 6.80002. Even though there are 3 zeros, they are still significant because they are in between the 8 and the 2, which are significant figures, making the zeros significant figures. The third rule states that zeros at the end of a number and to the right of a decimal point are always significant. For example, in the number that I gave here, 6.000, there are 4 significant figures. And this is because the zeros are used to demonstrate how persistent the number is. Therefore, they are very significant. The fourth rule states that leftmost zeros in front of a non-zero number are not significant. For example, in the number that I gave, 0.0075, there are only 2 significant figures, and that is the 7 and the 5. The fifth and final rule is that zeros at the rightmost of a number that lie to the left of a decimal point are not significant, and this is because these zeros are simply placeholders. For example, I gave the number 500, and we can assume that there is a decimal point at the end of 500. As you can see, there are 2 zeros to the left of the decimal point. So those 2 zeros are going to be not significant because we can write 500 in scientific notation as 5 times 10 to the second power. Let's talk about scientific notation. In scientific notation, a number is written as the product of 2 numbers, a coefficient and 10 raised to a power. The coefficient will always be between 1 and 10, and the exponent is always an integer. So how do we write 1,200 in scientific notation? We write that as 1.2 times 10 raised to the third. Now you might be wondering, how exactly did I do this? And I wanted to demonstrate that with the 1200 and the decimal and the squiggly line that you can see there, but unfortunately I had some difficulty working with the software and I wasn't able to do that. But the squiggly lines are supposed to be over the 1, the 2, the 0, and the 0 with the decimal point, because I wanted to show you how I moved the decimal 3 spots or 3 values to the left so that it could be right in front of the 1, because ultimately that is your goal, to only have 1 digit to the left of the decimal point. And then you raise your 10 to the number of times you moved the decimal point. That is why our answer is 1.2 times 10 to the third. If you have to move your decimal point to the left, that means that your exponent will be positive. However, if you have to move your decimal point to the right, your exponent will be negative. As you can see, I've inserted a chart of the International System of Units, or simply IS units, and these are the base units that are commonly used with prefixes to express measurements. And on the left we have the quantity measured physical property, the base unit, and the symbol. So for example, the base unit of mass is a kilogram, the base unit of length is a meter. For temperatures, we have Kelvin, and we have the symbol on the right. So the symbol for kilogram is kg, the symbol for meter is m, and so on and so on. And these bases are combined with prefixes that either increment or decrease the amount of the base. And I will show you that just in a bit. As I had mentioned before, this is a chart with the common prefixes used with SI units. And these are actually some of the most common ones, and they are giga, mega, kilo, hecto, deca. Then you have your base unit, you have deci, centi, milli, micro, and nano. And this chart also includes the symbol, the meaning, and the order of magnitude, because it's not only important to know the prefix, but to actually know its value and know that, kilo is 1,000. And I know this can be a lot to remember, so I just remembered the prefixes and I made kind of a little, well, it's not a song, but it's a phrase for me to remember it. And I start with kilo and I end with micro, and I say kings hate dragons because the B stands for base. Dragons can't make money. And when I'm taking a test or I just need to remember it fast, I just write that out, and then it's just easier for me to fill in the K, the H, the D, the B with kilo, hecto, deca, base, deci, centi, milli, and micro. It's easy, it's fast. Kings hate dragons because dragons can't make money. Dimensional analysis is a way to analyze and solve problems using the units or dimensions of the measurement. So let's say I want to know how many centimeters are in 300 kilometers. I'm going to start off by writing an equation in dimensional analysis. So I'm going to write 300 kilometers. The next unit I want to convert to is meters. So we can go back to our base unit, and then from our base unit convert to centimeters, which is going to be our final answer. So I want to go from kilometers to meters to centimeters. So I have 300 kilometers. Next, I want to convert to meters. So how many meters are in 1 kilometer? That would be 1,000. Now remember that you want your denominator to be kilometers so that the 2 kilometers can cancel out and you are left with meters at the top. So 1,000 meters are equal to 1 kilometer. Bam, you're done with 1 unit. Next, we want to convert from meters to centimeters. Again, there are 100 centimeters in 1 meter. Your meter is the denominator because you want your meters to cancel out, and you are left with the final answer. But this is done by multiplying all of the top divided by multiplying all of the bottom. So when you multiply 300 times 1,000 times 100, your answer is 30 million over 1, which is just equal to 30 million centimeters. You can also do this using days, minutes, hours, seconds. So I want to know how many minutes are in 4 days. So again, I'm just going to start with 4 days times how many hours are in days, because I want to convert from days to hours and to minutes to finally get my answer. So I go from 4 days times 24 hours, which equal 1 day, right? Making sure that day is the denominator so that I can cancel days out, times how many minutes are in 1 hour, which would be 60. So there are 60 minutes in 1 hour. Again, making sure that hour is the denominator so that I can cancel my hours out. Again, I multiply all of the numbers at the top divided by all the numbers in the bottom. So that would be. Finally, let's talk about density. Density is the ratio of the mass of an object to its volume. To do this, we can use the equation density equals mass over volume. It's very straightforward as long as you know the formula. You can plug in the numbers and you will always get your density. Mass is expressed in grams and volume in liters. So in many problems, your mass might be given in kilograms and your volume in milliliters. And this is when dimensional analysis is going to kick in, because you're going to want to convert from one unit of measurement into another. You're going to want to go from kilogram to gram or from milliliter to liter. So this is when you're going to have to use other things to make sure that your final answer is always written in the best form possible. In the example below, we are given the mass of 16 grams and the volume of 3 liters. If you plug it into your equation, your answer is 5.3 grams per liter. And this is just a short overview of some of the topics you should know to begin your chemistry class. I hope you enjoyed the video and thank you for watching.